there, wind energy students. Dr. John Schragi here, helping you wrap up Module 5 in our class. We're going to be learning now about one more factor that influences the local flow of any given location, and that's going to be what we're calling thermally driven flow. Now, when we're talking about thermally driven flow, we're talking about local circulations that are driven by the fact that, all else being equal, warm air tends to rise and cooler air tends to sink. Now that doesn't seem like all that much of an insight until you realize, well, different surfaces can have different rates at which they're going to be warming or cooling the atmosphere, which means there'll be different rates at which we're producing areas of rising air and cooling air and so on. And rising air and sinking motion, rather. So basically we have two main examples that we're going to be using in this class as our way of illustrating what we're talking about thermally driven flow influencing the local circulation. One will be the set of circulation features we call land breezes and sea breezes, and the other will be what we call anabatic and katabatic winds. They're by no means the only examples of thermally driven circulations in the atmosphere, but they are ones that certainly have power potential with regard to like energy production and so on. So let's start off by talking about the sea breeze and the land breeze. The sea breeze occurs at or quite near the coastline. On the order of a few tens of kilometers of a coastline would be where you'd expect to find a land breeze or a sea breeze. And sea breezes and land breezes are caused by the fact that during the day, land surfaces heat up a great deal more than the surrounding ocean surfaces do. Now, that can be a little bit hard for students to sort out as to why that would be. So let's talk for a minute here real quick about why we would have a very different rate of heating of land surfaces over the, of land surfaces versus ocean surfaces during the day. Now, your book actually only gives one good answer for that, and that is that there is a property of water, well, property of really any material called the specific heat. And the specific heat of water is much higher than that of land. In fact, they just throw out these numbers here that the specific heat of water is 4,186 joules per kilogram per Kelvin, and the typical value for like dry soil was more like 800 joules per kilogram per Kelvin. And they don't actually bother giving you much information as to what we mean by specific heat. Specific is one of these old creepy words in science that can be a little hard to sort out what they mean, but specific means per unit mass. So the specific heat is the amount of heat, well, let me give you a dictionary definition here. It is the heat required to raise the temperature of a unit mass of a given substance by a given amount, typically described as like 1 Kelvin. So the specific heat of a material is how many joules of heat it takes to increase the temperature of 1 kilogram of that material by 1 Kelvin. It turns out every material in the universe has its value of the specific heat. As it happens, the value for water is near 4,200 joules, and the value for other materials tends to be lower. In fact, the value for water is the highest of specific heat of any material in the universe that is likely to occur at like our temperatures and pressures. There's like liquid hydrogen and stuff like that that have higher specific heats, but water is the natural material you're actually likely to encounter that has the highest specific heat, meaning that it takes an awful lot of heat to change the temperature of 1 kilogram of that water by 1 degree. I mean, anybody who's gone and enjoyed a campfire already knew this. If you make a campfire and you put a kettle of water on to make coffee, and you also stick some marshmallows on a stick to make roast marshmallows, clearly the temperature of the marshmallows increases quite a bit more rapidly than the temperature of the water does. They're both absorbing heat from the flame, but the marshmallow will cook far faster before the water even begins really to heat up. So the same amount of heat from the sun, when the sun is shining on the surface of the earth, will change the temperature of the land a lot more than it'll change the temperature of, say, an ocean surface. And that's the only answer your book gives. There's actually more insightful answers we can give as to why the surface of the land will heat up more quickly than the surface of the ocean during the day. And part of the story is that water can cool by evaporation, much more so than land can anyway. We describe evaporation as a cooling process. This is why, mammals sweat, for example, is we put liquid water on the surfaces of our skin, and when it evaporates, it extracts heat from the surface of our skin and takes it up with it in the atmosphere. It's in the form of latent heat, for what that's worth. Well, the surface of the ocean, there's really no limit as to how much evaporation could be happening at the surface of the ocean. So there's a great deal of evaporative cooling at the surface of the ocean, a process that is keeping the surface temperature of the ocean from getting all that high, whereas there may be, and in fact typically is, evaporation off the surface of the Earth over land, but it typically can't be at the same kind of rate that the evaporation is happening over the ocean. So there is less evaporative cooling over land, and there is more evaporative cooling over water. A good reason why land will typically heat up more during the day than the surrounding ocean might. Also, there's another process by which the ocean surface can cool, and that is mixing. Mixing can bring cold, deeper water from far down in the ocean and mix it with the warmer, lighter water near the surface. Just to give you an example here, I just found this nifty little diagram online that gives typical temperature profiles in the ocean at 2 different times a year. The red curve is summer and the blue curve is winter, for 3 different regions of the world: tropics, mid-latitudes, and polar regions. And, just for illustrative purposes, let's focus on the tropical one, although this would work at any of them. But what you see is there's this big vertical gradient of temperature. There is, over a distance of a few meters, a big change in temperature, with the warmest water at the surface and getting colder as you go down. Okay? Well, what does mixing ever tell us about gradients? What mixing tells us is mixing gets rid of gradients. It tends to make it so that it's all the fluid that's being mixed has the same properties. We've seen that several times now this semester. In this case, when we have mixing due to the mechanical action of waves at the surface of the ocean, you are taking colder water from deeper in the ocean, not necessarily spectacularly deep, but a matter of meters down or something, and mixing it with the warmer water at the surface of the ocean, and that is a way of suppressing the temperature of the surface of the ocean. So we end up with these 3 ways that we are able to keep the surface of the ocean relatively cool during the day compared to the surrounding land. I mean, the surrounding land, for example, can't cool by mixing. If the sun is shining on sand on the beach, it can warm up the top layer of the sand, but there's no mixing going on in the sand that's taking the hot sand from up at the top and bringing it down deeper into the sand, and taking cool sand from down deep and bringing it to the top. That doesn't work. Only fluids can do that. So we have these 3 processes that are all working together to keep the surface of the ocean relatively cool compared to land during the day. In fact, especially the business of the mixing, and especially the business of the specific heat, less so the business about reason 2 about evaporative cooling, make it so that the opposite is true at night. At night, the water tends to be relatively warm compared to the land. An easier way to think about this is just to talk about the diurnal cycle. The diurnal cycle, or daily cycle of temperature over the ocean, is just not that great. Here we have 4 little diagrams just showing typical values of the diurnal cycle of temperature over the course of a 24-hour period at 4 different sets of conditions. In practice, there are about 4 different ranges of wind speeds. The diurnal cycle of the surface of the ocean depends a little bit on the speed of the wind, with windier conditions having practically no diurnal cycle, and less windy conditions, like up in the top left figure here, the wind having more diurnal cycle. But take a look at the scale here. Even in the top left diagram, which clearly has the greatest diurnal cycle of temperature of the surface of the ocean, the cycle's only a few tenths of a degree Celsius on average. It's rare that the temperature of the ocean might vary as much as 1 degree Celsius over the course of a day. What about the land? It can vary enormously. I mean, imagine when you go to the beach on a warm summer day, the temperature of the sand can be incredibly hot. It's too hot. Picture them walking across the beach. Ouch, 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 ouch. It's too hot, right? But at night, the sand is obviously not that hot. There's an enormous diurnal cycle to the temperature of the land, and not very much diurnal cycle to the temperature of the ocean. So the ocean is colder than the land during the day, and it is warmer than the land at night, at least under sunny conditions and so on. We're going to see that there's ways you can mess this up. But during the day, in general, the land is going to be warmer than the ocean, and during the night, the ocean is generally warmer than the land. And both of these temperature differences are going to be communicated up into the atmosphere, at least the lowest few tens of meters of the atmosphere or so by a process that we're going to call the sensible heat flux. We're going to be taking that property that the ground is warmer over the land than the ocean is, at least during the day, and we're going to be transferring that information about the temperature up into the lowest few tens of meters of the ground, above the ground, the lowest tens of meters of the atmosphere by sensible heat flux. Now wait a minute, let's make sure we're good on that word flux again. By flux, we're talking about like the, transfer of stuff. Previously we had like fluxes of kinetic energy, so we were talking about moving kinetic energy as our stuff. Here we're talking about joules of heat, sensible heat in particular, because it's the type of heat you can measure with a thermometer. It's not stored in like chemical energy or anything like that. So it's a transfer of stuff, joules of sensible heat, across a unit area per unit time. So we're going to have a flux of sensible heat coming out of the ocean and a flux of sensible heat coming out of the land through two little, unit areas, like I've kind of got drawn there on the plot there, per unit time. We're going to have transfer of heat. What's a nifty word to use for that? How about conduction? We're going to talk about this in terms of the conduction of heat from the ocean into the atmosphere, or the conduction of heat from the surface into the atmosphere. Now, this is going to be what the process is that's going to create sea breezes during the day and land breezes at night. Now, what I'm going to be doing here is I'm working with a little inset diagram that I've made over here that shows a cross-section across some kind of island or something like that. So you can see, like, this is a vertical cross-section. Down in the bottom left, you can kind of see some ocean water, and then we go across land, and then we go across some more ocean. There's a little cross-section. And for reference here, as we go up on the diagram, we're hitting lower and lower pressures. So you can see, like, for example, how high above the ground we have to go to get to 1,000 millibars, and then how high above the ground you have to go to 850 millibars, and how high above the ground you go to 700 millibars, and how high above the ground you go to 500 millibars, or something like that. Just kind of setting up this little diagram here across like a little tropical landmass or something like that, where we can have two different surfaces, namely the ocean and land, heating up differently during the day, because this is during the day, and we're going to see how that sets up sea breezes. What's going to happen is the land is going to be heated by the sun far more than the surrounding ocean is, and so the ground is being heated, and the heat from the ground is being transferred into the lowest few tens of meters of the atmosphere by sensible heat flux. Basically, we could say conduction, right? Relatively cool air is touching the relatively hot ground, and heat moves from the warmer object to the colder object. In practice in the atmosphere, it's a little more complicated than like what you learn in general physics about conduction, but it's not a horrible approximation to what's going on. Now, so the temperature of that lower atmosphere is going to be increasing. Now, as those layers of the atmosphere start increasing in temperature, they get thicker. They expand. Now, it's a little tricky to examine. You kind of got to look closely on the PowerPoint here. But notice only the layers kind of down near the ground are expanding and getting thicker. Okay, thicker like a thicker book. Okay, there's a bigger difference between the top and the bottom. See, for example, like look at the layer of the atmosphere between 850 and 1,000 millibars. See how over the ocean I have a smaller distance between the top and the bottom of that layer, but like over the land I have a bigger difference between the top and the bottom of that layer? That's because that layer has expanded. There's a nifty term in meteorology called the hypsometric equation, and we're seeing an example of that. That word is not important right now. So the layers near the surface have expanded over land during the day. The layers above there are actually the same thickness over the ocean over the land. I mean, look at that layer from like 700 millibars to 500 millibars. It is the same thickness, the same number of meters between the bottom and the top of the layer, whether we're over the ocean or we're over land. But it's higher above the ground over the landmass because it's been pushed upward. The layers below it have swelled to a thicker depth. They have expanded, pushing those layers up higher. But if you just pick any given height above sea level there, what you'll see is there's a big pressure gradient force, or PGF, at work. Because at that constant height, like where I've got those arrows drawn, over land the pressure is relatively high. Notice I've got like, I don't know, more than 700 millibars of pressure, like at the start of those two arrows there. Whereas, like, at the same altitude, but over the ocean, the pressure is lower than 500 millibars, we get a good pressure gradient force. taking air from over the surface of the land and take aloft, you know, a few kilometers above the ground, and transporting that air from the land towards the ocean. But here's the deal. Pressure is just the weight of the air above you. So the pressure at the surface over the land has to go down because actual mass up above us is being taken away from the land towards the ocean. So, I mean, pressure is instantaneously just the weight of the air above you. The pressure at the surface has to go down over the surface of the hot land, creating this area of low pressure. And because the winds are not going to be geostrophic at the surface and so on, we end up with flow that is going from the areas of higher pressure over the ocean towards the areas of lower pressure over the land. And that is our example of a sea breeze. Sea breezes are these winds that are at the surface. They happen during the day, and they have to go from the sea towards the land. We always describe winds in terms of where they're from. A sea breeze is from the sea. Notice it has to be during the day, and it has to be at the surface for us to call this a sea breeze. And it just got set up by this pattern, this circulation cell that we have established over our little landmass here, where the winds are coming in from the cooler ocean towards the hotter land. Let's see how we can make the opposite thinking work at night. So I got a moon here. We're looking at the cross-section of the atmosphere over this little island or whatever at night. And at night, the ground is going to get a lot colder than the surrounding ocean is going to because of all the kinds of reasons we talked about before. You know, it doesn't have to lose that many joules of heat by like radiation and so on for its temperature to change because its specific heat is low. And if the surface of the ground cools, like the sand cools at the top, there's no way, you can't take that cold sand at the surface and mix it with deeper, hotter sand. There's just no way to do that because it's not a fluid, and as a consequence, the ground will get colder than the surrounding ocean, and then by a flux of sensible heat, we'll be transferring heat from the relatively warm air into the cold ground, causing these layers of the atmosphere that are quite close to the surface to cool, to chill, and get less thick. They will shrink, they will contract. So if you take a look, for example, at the 1,000 to 850 millibar layer there, you can see how that layer is quite a bit thicker over the ocean, and over the land where it's cooling, they are getting less thick. And if you look at layers of the atmosphere that are higher up than that, like 500 millibars to 700 millibars, that layer is not, it's not touching the surface of the Earth. It's not mixing with air from the surface of the Earth. And as a consequence, it's the same temperature it was, but over the ocean and over the land, it's the same thickness, again by the hypsometric equation, but it gets closer to the ground over land because the layers below it contracted. They got thinner. They got less thick, to use the terminology in meteorology. But look again what that did, you know, in the middle troposphere or something like that for the pressure gradient force. Now, at any given height above ground, you know, a few kilometers up or something like that, we now have a very strong pressure gradient force from the ocean towards the land aloft. And therefore, we will have a flow of air from the ocean towards the land. We will be accumulating mass over the land mass there. The mass of air will be accumulating in the mid-troposphere. But remember, pressure is just the weight of the air above you. So if there's air mass accumulating above you, the pressure has to go up at the surface, and we get an area of high pressure at the surface, and that means that we will have flow spreading out at the surface. The wind is not going to be geostrophic because we're at the surface. We'll have a net component of the flow from the higher pressure over the land towards the lower pressure over the ocean, and we will get a land breeze. Again, a land breeze then is going to be occurring at the surface, at night, and it's going to go from the land towards the sea. What a very cool phenomenon there. Now, sea breezes are awesome, and if you live near the coastal region, you like them a lot on a hot summer day because they're a type of like natural air conditioner for these very hot coastal regions. Because once the sea breeze gets going, it's transporting relatively cool air from out over the ocean over your hot coastal region. You can kind of see it, it's even drawn on here as kind of like the leading edge of a little cold front. That's just kind of that little diagram there. That's just sort of for you to think about there. That's not actually a cold front or anything like that, but it kind of acts like one. It's a leading edge of some colder air from the ocean pushing over the relatively hot land. And that leading edge can penetrate on the order of a few tens of kilometers inland. Obviously examples where it has penetrated like hundreds of kilometers can be found, but a typical distance is like 25 kilometers or something like that. Let me show you an example here. Here's a picture from a satellite of a coastal region, and you can see the land where all those little puffy clouds are, and you can see the ocean where it's relatively clear. And wait a minute, why are all those little puffy clouds there? Well, it's sunny, and the ground is heating up, and heat is transferring by sensible heat flux from the ground into the atmosphere. We're getting warm air parcels that are rising. And we are getting, as air parcels rise, they can form clouds and so on. So we're getting all these little puffy cumulus clouds. It's adorable on there. Meanwhile, over the ocean, where the surface is cooler, the air parcels that are touching the surface are not all that warm. They're not likely to rise, and we're not getting the formation of clouds. Okay, so I can see my little setup here. And what I'm going to tell you here is there's a wind flowing from the ocean towards the land all along that coast right there. And you can even see how clouds are suppressed right along the coastline itself, because that's colder air from the ocean moving inland a few kilometers. So you can actually see how it kind of clears out right at the coast itself, because even though we're over the coast, that the air has not yet warmed up from contact with the surface of the ground, and so we're taking cooler air from over the ocean, and we're over land, but we still are relatively cold. These air parcels are not going to rise. You can kind of see how there's that leading edge of the sea breeze there. The clouds are a little bit enhanced there due to that kind of leading edge of that kind of almost like a cold front plowing forward over the land. You get the clouds a little bit enhanced. I actually like this diagram too, just because it illustrates it doesn't have to be an ocean or the sea that can create a sea breeze. This is actually Lake Erie, I believe, and a nice daytime picture of Lake Erie. And you have a lovely example here of a sea breeze coming off, I suppose people would say lake breeze, but it's the same idea, where the relatively warm land has all these puffy cumulus clouds, each one of which we can use as our way to visualize warm air parcels rising. And you can see how clear it is over the lake where the cooler air parcels are not rising. And as they go make a local wind from the lake towards the land, you can see how there's no clouds right along the coast there, where the flow is coming from the ocean, from the lake towards the land. And we are taking cold air over that region, and now there's those cold air parcels near the surface are not rising. In general, sea breezes and land breezes are kind of the opposite of each other, but they're not exactly equal partners in all of this. Generally speaking, sea breezes are more robust and more reliable and stronger and so on than a land breeze is going to be. Sea breezes are also relatively easy to disrupt. Remember, they're only part of the story of the circulation, but things like, for example, high clouds. If it's overcast with high clouds on a given day, well, there just isn't that much sunlight reaching the surface of the land. The land isn't going to get all that much hotter than the surrounding ocean, and we just won't see that much of a sea breeze going on. Clouds are a good example, especially overcast conditions, as creating a large-scale weather situation that kind of suppresses the activity of a sea breeze. Both of these patterns, though, the sea breeze and the land breeze, are just part of the story of winds at the surface in coastal locations. Clearly, all the other stuff going on larger scales matters too. Cyclones, anticyclones, fronts, hurricanes, thunderstorms, all that kind of stuff that's happening on larger scales matters too. It's only if the conditions are relatively light winds on like a synoptic scale or a global scale that we start seeing the importance of these microscale and mesoscale circulations. All right, before we move on to the second part of our lecture about thermally driven flows, which is going to be about katabatic and anabatic winds, let's answer a couple quick questions about what you've seen. Question 1. Water has a blank specific heat than dry land surfaces do. Higher, lower, or trick question, it depends on what the surface is made of. Interesting question. Make a choice of those 3 options and get a little feedback before you move on to question 2.